Swayam Prabha. Digital India. Educated India.
Hello everyone. So, in today's lecture we will continue with the Euler angles and ODFs, and we will continue understanding how we represent texture in terms of Euler angles and Euler space. So, in today's lecture I will start with showing the rotated cube component, right. We have observed the rotated cube component in the earlier lecture, and the rotated cube component is basically 100,011 component, and it looks like this as shown here, that the RD is on the RD, TD and ND of the rolled sample is given, that is the important sample reference directions, and X, Y and Z are the important crystal reference directions representing X by 100, Y by 010 and Z by 001. So, the position of the cube components basically are a rotated cube component are not shown here, but I will try to demonstrate it. So, you see that as in the earlier example of the cube component, we have kept RD, TD and ND of the sample reference system like this. In this case also we will keep it the same, but you see that in this case the position of the crystal axis, that is the X 100, the Y which is 010 and the Z which is 001 are somewhat like this. That is, it is at 45 degrees to RD and TD, that is X and Y are at 45 degrees to the RD, right. Now, if we consider to observe the first component along phi 1, phi 2, we can notice that if we rotate along ND by 45 degrees, then we are rotating the specimen axis by ND using the right hand thumb rule like this by 45 degrees to rotate the RD here and the TD somewhere here, right. So, you see that if we look after the rotation, the ND remains at the same position, whereas RD is somewhere here and TD is say somewhere here, right, at 90 degrees. Now, if such a situation, then RD is along 010, whereas ND is along 001. So, this texture which is 45 0 degree forms at a position where the Miller indices must be 001, RD 110, right. So, if we draw the ODF Euler space, basically let us start with drawing the Euler space, right, and the same Euler space that I have drawn earlier, I am drawing it here with this axis phi 1, this axis phi and this axis phi 2, right, phi 2 axis, and this is 0 degree, 90 degrees, 90 degrees and 90 degrees, right. Now, if we look into this, what we can see that if we give a 45 degree rotation along phi 1, that is a 45 degree rotation along ND, we can get the cube component, and the position of this cube component will be let me show it using the blue color, and this is here, right. So, this component forms at phi 1 equal to 45, right, phi equal to 0 and phi 2 equal to 0 section. Okay. Let us go ahead and say that if instead of giving phi 1 phi rotation of 45 0 and 0, if we give 0 0 and 45 degree rotation, then also the similar rotation will take place, and then along ND, and thereby the position of the rotated cube component will form at 0 along phi 1, 0 along phi, and at 45 degree, right, along phi 2, right, which is basically this one. The third situation that can happen is that if we rotate by 45 degree along phi 1, that is the first and the second first case, that is the first case, okay. And then if we rotate by 0 degree along the phi, and then again if we rotate by 90 degrees along phi 2, that means if we are taking this component and rotating along, say you are taking this R d, N d and T d, which is here, and if you are rotating N d by 90 degrees along phi 2, that is the phi 2 rotation, then what happens? The R d goes to T d, right, the R d goes to T d, and T d comes out like this, N d, R d and T d. So, R d becomes parallel to 1 bar 0 0, where T d becomes parallel to 0 1 bar 0 and N d remains parallel to 0 0 1. So, we could keep the specimen reference directions parallel to the important crystal reference direction 1 0 0s. So, you see 45 0 90 degree component will form at 45 0 phi equal to 0 and phi 2 equal to 90 degrees, and that is here. Now, if we look at the fourth situation, where we can see that if we rotate by 45 degrees, 90 degrees and 90 degrees, then what will happen? That we are taking this one, right, N d, and here was the T d, and here was the R d. So, we are rotating using the right hand thumb rule by R d by 90 degrees, which will make the R d will remain the same, and the N d will be somewhere now like this, and the T d will go up, right. So, this is the 90 degree rotation, and then what will happen, that if we rotate again along N d by phi 2 equal to 90, that is this rotation, right hand thumb rule, right, then what will happen, that this will become, R d will become here and T d will become here and N d here. So, you see that this time R d is parallel to parallel to 0 0 1, whereas T d is parallel to 0 1 bar 0 and N d is parallel to 1 0 0. So, this is also a position of the rotated cube texture component. So, this is at 45 degree to phi 1, 90 degrees to phi and 90 degrees to phi 2, and therefore, we can show this point using this blue color here, right. Now, let us take the fifth position, and the fifth position is little what you can say that little maybe tricky. That is, you see, (45°), 90° and 0 degrees. Now, you see that in case of the fourth this thing, I have given a rotation of 45° along phi 1, 90° along phi, and then again 90° along phi 2, right. I forgot that just by 90° rotation along phi, that is for the fifth situation, that is if we include only these two, and this becomes the fifth situation, that is, you see that in this case, after the phi equal to 90° rotation, the ND is basically parallel to 100, the RD is basically parallel to 010, and the TD is basically parallel to 001. So, this situation also exists at phi 1 equal to 45°, phi equal to 90° and phi 2 equal to 0°, that is this position. So, you see that we have found out 5 positions, and now we have to find out the one which is a little tricky. So, in this case what we need to do, we have to give a rotation of 90° along phi 1. So, we take this particular thing and then we give a 90° rotation along ND, and it can be shown like this: ND, RD, and TD is the initial situation of the specimen axis, and we are giving a 90° rotation along ND, which is phi 1 rotation, and then it will become something like this: ND, RD, and then it will become TD, right. So, you see the position of ND, RD and TD has changed. Now, if I cannot give any rotation along RD, because if we rotate along RD, then ND and TD cannot any way become anywhere near parallel to the specimen axis 100, 010, 001, right. So, we will not give any rotation along RD, rather we will give a rotation of 45° at phi 2 along ND. So, what we will do? We will give a rotation of 45°, and when we will give this rotation of 45°, what will happen? ND will remain at the same position, whereas the RD will change and it will become here, and the TD will form here. So, RD, this one, which becomes parallel to, you see, 1 bar 0 0, TD becomes parallel to 0 1 bar 0, and ND is always remain parallel to 0 1. So, this situation can be observed at phi 1 equal to 90°, phi equal to 0° and phi 2 equal to 45°, that is this position. So, you can see that the positions of the rotated cube texture component can be observed in the Euler space, and this position can be described in terms of, you see, the 100 pole figure, the 110 pole figure and the 111 pole figure, and the positions of the rotated cube component can be observed for the 111 poles here, and we have discussed this for the 110 poles here and for the 111 poles here, right. Now, you see that the rotated cube component has the rolling plane parallel to 100, that is the ND parallel to the 100 axis or the 010 or the 001 axis. So, 100 axis family. So, it can be shown here. The RD is basically parallel to 011. So, it can be shown parallel to 110, and if we cross multiply 100 with 011, we will see that the TD axis is also in the family of 110 axis. So, the TD can be shown here, and we have discussed this. So, now using, you see, this Euler space can be represented in terms of ODFs, right, ODF. Now, you see the positions where the the rotated cube component basically have formed. The rotated cube component has basically formed at phi 2 equal to 0 degree section, right, phi 2 equal to 45 degree section, right, and 90 degree section, right. So, we need to show all the phi 2 sections in this ODF, and we can just show this 3 sections, right. Give me a moment, I will make it better. So, this is 0 degree phi 2 equal to, this is, you see I am making 45 degree, and this is for the 90 degree section, and you see this is 0, 90, and this is again 0 and 90, and this is again 0 and 90 for the first, second and third orientation space, and this is also 90 for all of these boxes. So, this is phi 1 section, this is phi section for all of these boxes, and we can observe the position of the rotated cube component here, which is related to this one, and for this one we can observe it here, and the other 2 components can be observed from this phi 2 section. Let me show you the section, this section, and therefore, its position can be observed here and here. So, this one, and this one. So, on the other hand, the phi 2 equal to 90 degree section, which can be shown basically here, right, and in that case also we observe the position of the rotated cube components here, right. So, one can observe the Euler space and can calculate the position of the components in the Euler space, and this is another example showing rotated cube component. Now, let us go ahead and observe this situation for the Gauss component, and the Gauss component you can see that similar to the rotated cube component, we will be showing the specimen axis in terms of, you see, R d, N d, T d, whereas the sample axis in this case is basically, you see, 1 0 0, which is the x axis, say, or z axis, whatever it is, the x axis parallel, that is the, you see, we will consider it as 0 1 0, and then the y axis we will consider it as 0 0 1. So, to just make you understand, it is something like this, right. So, this is one plane and this is another plane. So, the components are like this, right. Now, you see that the position of the Gauss texture components were shown in the Euler space that we demonstrated by these orange components, right, these components, right, these are the Gauss texture component. The Gauss texture component is basically 1 1 0 parallel to the rolling plane and 0 0 1 parallel to the rolling directions, right, and it will look similar like this as shown in this figure and can be demonstrated like this. Now, let us consider the situation where we are going to find out the Gauss texture, and so the situation 1 is that if we rotate the specimen axis by phi 1 phi 2, say we rotate initially by phi 1 by 0 degree, and this is the first case, and then if we rotate phi by, you see, 45 degrees, because you see phi rotation is along R d, and therefore, we are giving a 45 degree rotation using the right hand thumb rule, and which is basically like this, right. So, this is the rotation that we are giving along R d, and therefore, what will happen that the R d will remains the same and T d will go a little above like this, and ND will go here, right, if it is following this same, just the yellow color I am showing to demonstrate the 3-dimensional nature of the construction, right. So, you see that TD is now parallel to 0 1 0, the ND ND and the TD. So, TD is parallel to 0 1 0, the ND is now parallel to 0 0 1 and RD is parallel to 1 0 0. So, the position of the angles phi 1 phi 2 could be traced to 45 0 45 and 0. Therefore, if we make the the Euler space here again, (0 degree, 90 degrees, 90 degrees, 90 degrees, and this is phi 1, phi, and this is phi 2, right. So, you see the position can be traced for the Gauss texture component, and that is basically 0 45 and 0. So, 0 and along phi 1 and 45 along phi and 0 along phi 2. So, the position is basically this one, right. So, if we take the second situation, and then what we just know that if 45 degrees can go phi, at phi, then at phi 2 if we rotate by 90 degrees, then you see the texture, the similar texture can be obtained. So, what we are doing, we are basically taking this first one and adding a rotation at phi 2 equal to 90 degrees, right. So, how we will do so? We will take this, we will rotate it by 90 degrees, and when it will be done, what will happen? The TD will go somewhere somewhere here, and the RD will go somewhere here. So, this is TD after the rotation. So, the rotation is taking place like this. So, the RD is going to, let me delete and make it once again for clarity. So, ND remains the same, the RD goes to TD and the TD goes to opposite of RD, right. So, under this situation you see the ND remains parallel to 0 0 1, the TD which was I have written it wrongly, that earlier it was TD and now it became RD, remains parallel to 0 1 0, and the TD becomes parallel to 1 bar 0 0. So, we have traced the specimen axis from the Gauss texture component to the position where the important specimen axis are parallel to the important sample axis, and thereby this position 0 45 and 90 degree is also the position of the Gauss texture component. Now, what is 0 45 90 degree? So, phi 1 0, 45 along phi and 90 degrees along phi 2. So, this is the position, and so this is the position that we have shown earlier. Now, the third position of the rotated cube is basically, you see, if we rotate phi 1 by 90 degrees, and let us take this first one ND, TD and RD, and let us rotate by 90 degrees by ND, and then what will happen? Then RD will go, let us use the perfect color RD. So, ND will remain at the same position, RD will rotate like this and go here, and TD will rotate and come here by 90 degrees. So, you see this is the first rotation, and then again if we rotate along phi by 90 degrees. So, what we are doing? We are doing a right hand thumb rule rotation along RD, and thereby the R d remains at the same position R d, and the N d is rotated somewhere here and the T d is rotated here. Now, you see that still we have to rotate to go to this position. So, the sample has to rotate still to go to the specimen axis. So, if we rotate by N d along by 45 degrees. So, using right hand thumb rule, this one. So, right hand thumb rule, and thereby the rotation will take place such a way that R d will rotate somewhere here and T d will rotate somewhere here, right. So, instead of drawing it here, let me remove this slowly and let me draw it separately. So, N d remains the same and R d and T d are forming something like this, right, T d and R d, right. In order to for you to realize the 3-dimensional nature of this construction, I am drawing this yellow color, and then you see that R d is basically you see parallel to 0 0 1 bar, T d is basically parallel to 0 1 bar 0, whereas N d is basically parallel to 1 bar 0 0. So, this position 90 90 and 45 degrees can be seen in the form of the position phi 1 90, phi 90 and phi 2 equal to 45. So, these are the position where the Gauss texture components basically develops. Now, you can see that the Gauss texture component, which is the 110001 texture components, can be observed in the Euler space like this, right, in these positions. So, instead of showing them in the Euler space, what we would like to do is that we show that in terms of ODF at phi 2 sections, right, like the other ones. So, what we will do is that we will draw important phi 2 sections. We see that the Gauss texture is observable at phi 2 equal to 0 degree section. It is observable at phi 2 equal to 45 degree sections and phi 2 equal to 90 degree sections. And then if this is 0 degree for phi 1 to 90 and the same for the other ones, and this is phi from 0 to 90 and same for the other ones, the positions of the Gauss texture components can be seen as, if you say for example, we sliced along phi 2. So, this is the first slice, and so the component can be observed here, which is basically this position. On the other hand, when we do the second slicing at 45 degrees, that is this slice, right, the component is observed somewhere here, which is basically this position, right, this position, and I am showing with a large spread, as usual will happen in case of real life scenario. On the other hand, for the phi 2 equal to 90 degree section, the slice is actually the lowest one here, and the position is here, which can be shown here. One can see that the symmetry of the cubic crystal always will show that phi 2 equal to 0 and phi 2 equal to 90 degree section will show the exact same component at the same positions, and this is related to the symmetry. The position of the Gauss texture components in terms of pole figure and inverse pole figures are already discussed, and see in terms of the pole figure, here we have shown to compare for you the positions for the 100 poles, and you can see that it shows a two-fold symmetry, because the N d is here and the N d is 110, which has a two-fold symmetry, and you can see the 110 poles too, where at the center we can see the position 110 as N d, and here is the 111 pole figure. So, one can observe from all this pole figure a two-fold symmetry. At the same time, one can observe the inverse pole figures, and as the Gauss texture component has 110 parallel to the rolling plane, that is the 110 axis parallel to the normal direction. So, you can see its position here at 110. So, the ND inverse pole figure. On the other hand, if we look at the rolling direction, which is 001. So, the RD pole figure inverse pole figure shows its position here, and then a cross multiplication or cross product of 110 cross 001 gives the position of TD, which is here. So, we see that one can relate the inverse pole figure and the Euler space, and can find out the position of various texture components. Of course, these are easier ones by simple rotation using the geometry of the sample axis and the crystal axis. Just the rotation should follow the Euler's angle principle given by the Bungé, that is the Bungé's way of rotation phi 1 phi 2, so that the specimen axis could be rotated and go to the crystal axis of that particular kind of texture, and in this case what we have shown here is for the Gauss texture. Earlier we gave the example of rotated cube and cube texture, and that is all for this lecture in the today's class. Thank you.